Thank you very much. Let me thank all the organizers of this school. I enjoy very much being here, and I've seen that there are many participants, so it's quite a successful school. So the point of this lecture is to compare MUSR with other magnetic resonance techniques. There are many. There is the nuclear magnetic resonance, there is the beta NMR, ESR, so it's quite a broad topic, and what I will try to give you is to present the experiments where MUSR can say something more with respect to his other techniques. So I will, let's say, give you a flavor of where MUSR is more advantageous rather than, let's say, NMR or ESR or the other. So if we start from the beginning, what are we doing with magnetic resonances? What we do basically is to study the time evolution of the muon polarization, of the nuclear magnetization, of the electron spin polarization in general. And what is determining this time evolution are the Hamiltonians to which all these particles, this probe, are interacting, and are, let's say, this interacting Hamiltonian to which all these particles are sensitive. And if we take, for example, just to start with the NMR, so the nuclei, and which are present both for the NMR nuclear magnetic resonance and the beta NMR technique. In general, the nuclei are sensitive to the Zeeman Hamiltonians, namely the interaction with an external magnetic field, if we apply a magnetic field. We are sensitive with, let's say, nuclear dipolar Hamiltonian, the interaction between nuclear magnetic moment dipoles. We have the hyperfine interaction between the nuclear magnetic moments and the electron magnetic moments, so this nucleus-electron hyperfine interaction. And there is also, for those nuclei which have a spin larger than 1/2, this electrical dipolar Hamiltonian. Now, the muons are basically, in the MUSR experiment, sensitive to all of these three first Hamiltonians, except the last one, because the muon is a spin-1/2 particle, so it doesn't have an electrical dipole moment. And so basically, if we apply magnetic field in the MUSR, we'll have this Zeeman splitting. There is a dipolar interaction between the muon magnetic moment and, in general, the nuclear magnetic moments which are present in your system. And the, let's say, more interesting part in general to study the properties of a certain material is this hyperfine Hamiltonian. At the end of this talk, actually, I will show you that with MUSR, you can even probe this part. So basically, let's say that these Hamiltonians that we can probe and the interaction that we can probe with MUSR are rather similar than to the ones that you can probe with NMR or with beta NMR, which is, as I will show you in a moment, basically very similar to nuclear magnetic resonance, except that you put your nuclear probe inside with, I would say, an ionic beam. And given this, at the end of the day, the quantities that you are measuring with nuclear magnetic resonance and MUSR are rather similar. For example, you can measure an I shift, namely the shift of the Larmor frequency that you have in your material with respect to the vacuum. You have a time evolution of your, let's say, nuclear or of the muon polarization, which is determined by basically two quantities. One, which is the mean square amplitude of the field fluctuations, and the other, which is the characteristic correlation time, tau c, of this fluctuation. This is the same for NMR, for beta NMR, and for MUSR. You can measure spin lattice relaxation rate, and this is what you can measure both in NMR and, if you want, with a longitudinal experiment in MUSR. So at the end, there are many similarities. And so the difference when to use one approach or the other depends a lot on the particular experiment you want to do. Well, there are some very relevant technical differences that at the end tell us when it is more convenient to do a type of magnetic resonance or the other. Here I have summarized just some of them. And in green you have, let's say, situations where it is more convenient to do a certain technique, to use a certain technique, and in red, let's say, the drawbacks. So the advantage of MUSR and of beta NMR is that they exploit the beta decay, so that you detect either a proton or an electron with certain detectors, while the NMR and ESR are basically based on electromagnetic wave detection. Here there is a B missing. And this is a particular problem when you are dealing with metals and superconductors, because you have a problem of penetration depth of a radio frequency, or even worse, of a microwave. So basically, this is telling us that if you're doing an ESR experiment in a superconductor, at the end, it is very difficult because you will probe just a very thin layer of the surface of your material. While with MUSR, we don't have this problem. I mean, we can probe the whole sample, the muons go through all the samples, and the positrons which are emitted, you can detect them very easily coming from all your sample. The other advantage is that in these techniques, MUSR and beta NMR, you are able to produce a highly polarized beam of particles, spin polarized beam of particles, while in the case of ESR, or if you want of NMR, bipolarization comes from the thermal magnetization. And considering that the Zeeman splitting that you have in the, let's say, NMR experiment is very small, and in particular is much lower than the thermal energy, at the end of the day, the polarization that you get in an NMR experiment is of the order of 10 to the minus 5, which is basically telling us that just one nucleus out of 100,000 will contribute to your signal, while in the MUSR, all the muons will give you a signal and contribute to your polarization. So let's say this is standard, let's say, NMR, and in standard NMR we have this problem of low polarization. Of course, there are many techniques that can help to improve this even in nuclear magnetic resonance. And the other point is that if we want to produce a polarization in an NMR experiment or an ESR experiment, we need to apply a magnetic field. While in MUSR or beta NMR, you already have the 100% in MUSR polarization of the muon spin, even without applying an external magnetic field. And this allows you to perform the zero field experiment quite conveniently. So these are, let's say, two main points where these two techniques have some advantage. Beta NMR is, of course, something in between, because in beta NMR you have to use also radio frequencies. But MUSR certainly have these two big advantages. And the other big advantage is that you have listened to the Suter yesterday talk on low energy muons. And with low energy muons or with beta NMR, you can conveniently, produce a beam which can penetrate only down to a few nanometers and then study thin films of different materials. While typically, but it's not always the case, in NMR and ESI, you are working with bulk samples. However, there are some drawbacks. So let's say for beta NMR, the problem is that you are putting inside your sample a big nucleus. Let's say, usually it's a low atomic number nucleus, like, for example, lithium, but still is a big perturbation to your system. And so, in the case of beta NMR, what you are introducing with your beam is a non-negligible perturbation. It can cause defects, and so that's a drawback. Another drawback of these two techniques with respect to NMR and ESR is that, of course, they are much more expensive than this one. On the other hand, NMR and ESR, you are probing equilibrium conditions, so you are applying extremely weak perturbation, either with radio frequency or with microwaves. It's not always the case, but most of the time it is like this. And of course, they are much older than these techniques, and so they have been much more developed in the, let's say, last decades. So these are some main technical differences, and based on these technical differences, we should see some of the cases where MUSR is more convenient than the others. Before going to these examples, let me show you also another important comparison between what you can study with one technique and the other. And usually one point that one makes is which is the characteristic time scale that one can probe with muons, with respect to nuclei, with respect to electrons, and so on. Well, you can find in the literature, and for example at this site here, this drawing where you have a MUSR which can probe this, let's say, from 10 to the minus 4 seconds to 10 to the minus 12. But this should be taken with care because it's quite indicative in the sense that with MUSR, in principle, depending on the type of experiment you want to do, you can probe even, let's say, dynamics which are of the order of a second. You can probe dynamics which are even faster than 10 to the minus 12. And by the way, if we compare this to nuclear magnetic resonance, one would say, okay, where are we with nuclear magnetic resonance? In principle, you can probe all this range without big problems with the NMR. Of course, from this, you see that I am an NMR guy. But the point is that at the end, there is no problem in measuring relaxation rates which last hours, and there is no problem in measuring, let's say, dynamics which are of the order of 10 to the minus 14. It has been done in many cases, and it depends a lot on the experiment. So this comparison of time scale should be taken with care, and it depends a lot on which type of experiment you are doing. For example, there is a nice review by Sugiyama on the study of ionic diffusion in materials which are relevant for batteries and for energy storage. And there is this comparison which is related to the characteristic time scale for ionic diffusion in different materials, either in solids or in liquids. And in that case, basically, the time scales you probe with NMR are in this range, with beta NMR are here, with quasi-elastic Newton scatter here, and with MUSR, basically, you probe this time scale. So this is okay, but it is, let's say, a nice comparison related to ionic diffusion. What is important when we compare these different techniques is a big difference that you have between local probes like nuclei, muons, and electrons, and non-local probes as the neutrons. And the difference is that with the local probes, as we should see in the next lecture that will be in the afternoon, what you are probing is the Q integrated, so the integral over the Brillouin zone of all Q excitations, while with neutron scattering you can be Q selective, and so you can probe each excitation at each Q wave vector at a time. So this is an important difference that I want to report. So these general remarks should be taken with some care. I made them, and now what I want to do is to show you some examples where you can do MUSR, but the other techniques are not possible, or they have some drawbacks. And so some good motivations why MUSR should be done. And in this, I will give you some examples. So, first example is when it is more advantageous to do MUSR. And the point is, for example, when you don't have a good local probe already inside your system. For example, you don't have a good nucleus. What is a good nucleus? Well, typically, a good nucleus means a nucleus which have a high natural abundance or a high magnetic moment, namely a high nuclear gyromagnetic ratio. For example, suppose you want to you have a system where you have plenty of oxygen. You cannot study oxygen 16 because it's a spin 0. Okay, oxygen 16. You could think about using oxygen 17, but if you look at the natural abundance of oxygen 17, it is very low, so very poor NMR signal, you cannot do NMR. Or for example, you don't have unpaired electrons, and so if you don't have unpaired electrons, you cannot do ESR. Well, one could say, okay, why to do ESR? I can try to do beta NMR. So I put some of these nuclei inside my sample. For example, the most used is at this lithium-8 nucleus. And then you can use some of these nuclei provided they have, let's say, a reasonable decay time, which is of the order, let's say, of a second. They have a very high asymmetry, so basically the beta NMR experiments are based on a beta decay and on the emission, for example, here of an electron which is detected as in a positron in the MUSR experiment. And however, when I put all these nuclei, I'm not making a small perturbation to my system. I can even create defects. Of course, this can be relevant, for example, if I don't know, I want to study pinning centers in superconductors, and I want to produce defects, and I can use the probe which produces these defects, okay, to study the effect, for example, of these defects on the pinning of the flux lines in superconductors. Or, for example, another case where it can be relevant is to study ionic diffusion in certain systems. If I want to study lithium ionic diffusion, I can put the lithium inside, okay? And then I can study with beta NMR the diffusion of lithium. But still, in general, it's not, as I said, a small perturbation. If you want to learn something more, there is this nice review by Andrew McFarlane on beta NMR. So suppose we do not want to perturb our system, we don't have a good nucleus. So what we can do is to do MUSR. For example, in this system, with cerium and ruthenium are not good nuclei. If I want to study the system which is a superconductor, the flux line lattice, as you have learned by Roberto De Renzi, it is also superconductivity. When you enter the superconducting state, if it is a type 2 superconductors, you have flux lines entering, and so if the field is applied along this direction, there is a modulation of internal field which gives rise to this distribution of the field inside the sample. And there is a broadening then of your spectrum, of your MUSR spectrum. And you can, let's say, measure your spectrum by making this Fourier transform of your MUSR signal in transverse field, and then you can study, for example, the temperature dependence of this broadening, which is associated with the temperature dependence of a Landau penetration depth. So in this system, you can do it just with MUSR, okay? You cannot do NMR nor ESR, because ESR does not penetrate the microwave inside your system. So this is an example. Another case where it is much more relevant to do MUSR rather than techniques as nuclear magnetic resonance. Well, the advantage of MUSR is that you can measure relaxation rates which are quite fast, while typically if you do, for example, NMR, okay, you cannot access relaxation times which are below usually 10 microseconds, something like this. This is just because of some technical aspects related to pulsed nuclear magnetic resonance. And so in this case, okay, it is convenient to do a MUSR experiment. Let's give you some example. Manganese 12, I don't know if all of you know, but it's a well-known molecular magnet. So it is a solid where you have a molecular solid where you have plenty of these molecules. You have a lattice of these molecules. And these molecules are decoupled one from the other. At low temperature, this molecule ends up in a total spin S equal 10 ground state. And you have a progressive slowing down of the spin fluctuations. So we started to study this system with NMR. Okay, in particular with proton NMR, since you have plenty of proton here. And what you have if you do NMR is that you can measure the relaxation rate, so the if you want the 1/T1, the spin lattice relaxation rate down to a certain temperature. But then you lose the signal because this relaxation time, this relaxation rate is too fast. So what you can do is then to come to, in this case it was done I think partly at ICES and partly at PSIs, to do MUSR. And since MUSR you can access much faster relaxation rates, you can start to do MUSR. And you follow the same trend and you pass through a maximum, which indicates that you have a slowing down of fluctuations which reaches the Lamarck frequency. And so in this case, we could study well the temperature dependence of this spin dynamics associated with slowing down of fluctuations in this molecular magnet. Another example, this is a heavy fermion compound, which is very close to a quantum critical point. Again, also in this case, we started to do, in this case, is copper nuclear particular resonance, so it's basically like NMR, but is in zero field and associated with transition between the level split by the particular interactions. In any way, we measure 1/T1 on this nuclei, but we could measure it only down to this temperature, let's say about 1-2 Kelvin, because then the relaxation rate was too fast to be measured with, let's say, a nuclear resonance technique. So what we did is to then go to BSI and to do the experiment. This is in zero field. We did zero field USR, and to study the longitudinal relaxation rate in, the zero field relaxation rate here. And we saw this, let's say, divergence of the relaxation rate to very high values. So this could be done only thanks to the fact that MUSR allows you to estimate very fast relaxation rate. And let's say this is a behavior one expects close to a quantum critical point for this heavy fermion compound. Well, another relevant case where it is much more important to do MUSR, as I already mentioned in one of the first slides, is that you can do zero field experiments. And this is because you have already a fully spin polarized beam. While in the case of magnetic resonance, as nuclear magnetic resonance or ESR, you have to apply a magnetic field to generate your magnetization, which at the end will give you your signal. And of course, to do zero field experiment is very relevant in systems where the magnetic field cannot be used just as something which helps your technique, but is something which is perturbing a lot your system. So if you want to study your system without perturbing it with a magnetic field, it is necessary to perform a zero field experiment, and this can be done with MUSR. For example, if we go back to our molecular magnet, to our manganese dual molecular magnet, what we have is that if you do not apply an external magnetic field, you have a splitting of the levels, which can be labeled by the Z component along the anisotropy axis of the spin, S equal 10, and this splitting is associated with the magnetic anisotropy. So basically, in zero field, you have just this term, and so you have ms plus 10 minus 10, minus 9 plus 9, and so on. Now, if you want to study the dynamics of this system, you know that if you apply a magnetic field, what will happen is that you will induce a Zeeman splitting of these levels, and so the energy level splitting of this level will change because of this term. And of course, the dynamics that you will probe by applying an external magnetic field will be different with respect to the one that you have in zero field, where you have only this term. And so in this case, which are basically the data I showed you in a slide, let's say a few minutes ago, it is very relevant to study the system also in zero field in order to avoid this unwanted effect of the magnetic field. Another example, these are, let's say, a family of organic conductors which goes under the name of Beshar salts. So you have a quasi-dimensional organic conductor where you have a stacking of these TM-TSF molecules, which gives rise to a high conductance along this direction. And what happens at low temperatures is that in these systems, you can have a spin density wave phase or a superconducting phase. The point is that in certain of these systems, this superconducting phase can be quenched, and you can have a spin density wave phase which is induced and strengthened by the magnetic field. So the magnetic field is affecting the ground state of the system. Okay? And so how to probe the system in zero field before I perturb it with a magnetic field which can induce this spin density wave phase? Well, with MUSR. And this is what we did in this work, Leia and co-workers. And we studied different families of these organic conductors. And what they measured in this case here is the spin density wave order parameter just by making zero field MUSR. Okay? Another example. Okay. I recall again this heavy fermion compound I have already shown in a past slide. And in this heavy fermion, if you are quite close to a quantum critical point, you can make the system switch from a non-Fermi liquid to a Fermi liquid behavior by applying a strong magnetic field. Well, not even strong, just a few kilogauss. And this is, for example, the case of this system. If we do zero field MUSI, we can see, let's say, this divergent behavior of the longitudinal relaxation rate in zero field. But if we apply a magnetic field of a few kilogauss, we see a completely different behavior. And okay, this is not easy to see because this is a double logarithmic scale, but this is a linear behavior plus a constant, okay, which is the behavior that you expect for the relaxation rate in a, let's say, ideal method. Okay, so besides this, there is another good reason that I have already mentioned where MUSR is more convenient rather than, let's say, NMR and ESR. And this is the case when you are dealing with metals or with superconductors. And the reason why is, as I have already mentioned, is that if you are dealing with a superconductor, for example, the radio frequency field or the microwave field will penetrate just for the, so let's say, for the depth, which is of the order of the lambda penetration depth, which means, so let's say, a few thousand angstroms. In general, it can be a bit more if you have some flux line motion. And of course, as probably Roberto De Renzi has explained to you, with MUSR, one can learn a lot about the properties of superconductors. And let's say one of the most beautiful results that was obtained with MUSR in the study of superconductors, in particular of high DC superconductors, was the setup of this so-called Uemura plot. So just to recall you, what you basically do is to study the temperature dependence of the transverse field relaxation rate as a function of temperature. These are two high DC superconductors, and when you enter the superconducting phase, you have, because of the presence of the flux line lattice, an increase in the relaxation rate, which is associated with the fact that you have a certain modulation of the local field induced by the flux lines. And the point is that at low temperature, this quantity is basically proportional to the amplitude of the field modulation, which is directly related to the inverse of the lambda penetration depth squared. Okay? And Uemura, he first proposed this plot where one can plot Tc as a function of sigma, the transverse relaxation rate, or if you want, as a function of the inverse of the square of the lambda penetration depth, which is basically proportional to the density of superconducting carriers. And then, since there is some linear behavior, okay, there started to be some speculation about proportionality between Tc and the Fermi energy for 2D electron gas, since for the 2D electron gas, the number of superconducting carriers is proportional to the Fermi energy. But anyway, it's a nice way to analyze the properties of superconductors. And this you can study well if you do MUSR, not if you do NMR. Of course, let's say more recently there has been, let's say, different studies of this system that have put, let's say, some remarks on this Uemura plot. But anyway, it's a very nice way to analyze
the properties of superconductors and also to understand if, for example, one is close to Bose-Einstein condensation limit or not. And the point why one cannot study this with NMR is basically, as I told you, because of the radio frequency penetration problem. So what I did in this study is to take, for example, this family of high TC superconductors and do yttrium NMR in the system and measure in the superconducting phase the modulation of the local field, which is proportional to sigma, to the transverse field relaxation rate. And what I obtain with NMR are these points. There is one point here. But if you do μSR, you see something which is here. So you probe a modulation which is much smaller than the one that you probe with μSR. Basically because the radio frequency is penetrating just on the surface of your sample. And so, let's say, NMR has this problem, and this is why, again, it is convenient to do μSR. The other point which I would make is that when you do NMR, of course, you have to apply radio frequency pulse to, let's say, perturb the system and see and study the time evolution of the nuclear magnetization. And when you apply radio frequency pulses, if your flux lines has a certain mobility, what you do is to shake your flux lines, okay? And so your radio frequency pulse can induce a certain mobility of the flux line lattice and induce a non-negligible perturbation. Just to show you that indeed with NMR we are not probing the full sample. What I report here is the amplitude of the NMR signal in this family of superconductor as you go below TC. And as you go below TC, what you see is that the intensity of your NMR signal decreases down to about, let's say, 10–15%, which is basically telling you that you're probing just 10% of your sample because of this problem. This is not a problem for μSR. And this is why, basically, μSR has been, let's say, the most used technique to study the flux line lattice in superconductors. Okay. Another relevant complementarity of μSR with respect to other techniques is that, let's say, in most cases, you have a mu plus which goes in interstitial position, okay? And, for example, if you probe the muon shift of the mu plus which goes in interstitial position, this shift is related to the amplitude of the electronic wave function at this interstitial position. While with the nucleus, you probe the amplitude of the electronic wave function at the nuclear side. So there is also this side complementarity between nuclei and muons. Maybe I will not finish this talk because Adi showed me that I have still 5 minutes, but since there will be another hour in the afternoon, I will maybe continue this part and then talk about the complementarity between muons and Bulk techniques. Okay. When μSR is still relevant? Well, if you want to study in zero field, without perturbing our system, magnetic order parameter. And this is, for example, in the case of an antiferromagnet, we can study well the critical exponents. We can study, for example, the reduction of the magnetization at low temperature. This is just a zero field μSR in these two systems. This is the temperature dependence of the local field at the muons that you can study. And you can study well this order parameter. And if you concentrate on the low temperature, for example, you can study, before going to the low temperature, this is to compare with an NMR. In NMR, again, I have to apply a magnetic field if I want to make this study, okay? And if I apply a magnetic field, I will perturb the system, in particular in this case, where the system has an exchange coupling which is of the order of a few Kelvin. So it is a non-negligible perturbation with NMR. And the other point I want to make is that with NMR, for example, to study the order parameter, what you're going to measure is the splitting between these NMR lines, which are, let's say, you can define not so well as you do for the μSR internal field. So you get a big error bar here with respect to the case of mu-SR. The other point I want to make is that, as you know, the mu plus will mimic what is basically a proton, a light proton. And so with studying the mu plus, one can learn a lot about, let's say, the chemistry and the properties of organic systems, or system where instead of putting, let's say, an H plus, you put an alkali ions. And this, of course, you can do with mu-SR, not with other systems. Just to give an example, this is a phthalocyanine molecule. So basically, you have an organic solid made of these flat molecules. And if you study the system which is zinc phthalocyanine, so you don't have sodium, okay? What you end up is that you form a lot of muonium. So if the mu plus get attached to one of these sides, and to know how much is the fraction of muonium that you get into this sample, what you can do is to study, for example, the recovery of the asymmetries of the magnetic field, and from this study you can have an idea about the fraction of muonium that you are forming. What happens is that if we put sodium inside the system, this fraction of muonium dramatically decreases. And this is telling us that what is basically happening is that the sodium is getting attached to one of these sites where the mu plus was getting attached to form muonium. And so we can learn where, let's say, and have an idea where the sodium is going to be placed in the system. Okay, I will finish with this, and then I will continue with a few examples later on, so that you may ask questions. Of course, we have a big advantage in the development. Okay, this you had 2 hours on this talk yesterday. Is that low energy muons is a very powerful technique to study thin films. And just to give you an example, this is again a molecular magnet. This is terbium phthalocyanines. And in this study, that was done, of course, at LEMS, so at ESI, what we managed to learn is by studying the relaxation rate of muons which are implanted at different depths. So in one case, close to the gold substrate, and in other case, far from the substrate, is that the dynamics of the spins of this terbium in this organic molecule was quite different close to the surface. The dynamics was much faster rather than, you see a turtle here. Okay, of course, it's not present in the sample, but so the dynamics here is much slower. And this is a nice application of low energy muons. Of course, you can use this type of techniques very similarly also in the case of beta NMR. And indeed, the beta NMR is a technique where the nuclei which are implanted in your system penetrate just a few nanometers, okay? And so it can be indeed useful to study, for example, in this case here, topological insulators. In this respect, it is very similar to low energy muons. And so you can study, let's say, the difference between a topological insulator between surface and bulk, and so to distinguish the metallic and insulating behavior. But again, keep in mind that the muon is a much smaller perturbation with respect to the lithium ion which are put inside. Okay, this can be done with beams of muons, beams of nuclei. Can we do it with NMR? Can we do it with ESR? Well, usually not, but of course there are many advanced, many, let's say, developments of NMR, which are, for example, nuclear magnetic resonance force microscopy, which is basically a nuclear imaging technique based on the use of a cantilever tip, where you have a sample which is at the end of the tip. With your nuclei, you apply radio frequency field and you have here a small magnet which is close to the end of your tip. And you can perform, let's say, in this case, NMR experiments on something which is of the order of 10 nanometers thickness, for example. And so let's say that if one wants, one can do also NMR in very small sample. Of course, the point is that it's a very tricky experiment. Actually, in Europe, for example, there are only 2 groups performing this type of experiments. One is Martino Poggio in Basel, and the other one is Osterkamp in Leiden. So, I mean, one can do this, but it's very hard work. And if you want, more recently, one has found also nuclear magnetic resonance of a single nuclear spin. So very impressive, but again, is something which is not at all trivial. And the point here is that one can make the study of a single nuclear spin by exploiting the fact that you can couple this nuclear spin to the electron spin in diamond MV centers, and then by, let's say, studying these MV centers, you can get information on the nuclear spin. So these are all, let's say, recent developments of NMR, but it's not, let's say, standard approach. It's rather, let's say, tricky and, I mean, not what one can learn. So I will stop here. I want to tell you a bit more about, to finish the story on this comparison between NIRASAR and magnetic resonance techniques, and then in the afternoon go on also with the comparison with between muons and bulk techniques. Okay, thank you.
I'm sure there are many questions. Maybe I should not be so sure. Pietro, one of your early examples on the heavy fermions, it looked like there was a, when you were looking at the 1 over T1, T2, I think the first example. There's an offset.
Yes, yes. I mean, okay, this offset is not between.
Sorry.
No, okay.
Yeah.
Anyway, you have also NIRASAR data which go up here. What is this change of slope? I cannot tell you.
Okay.
There is indeed a change of regime between, let's say, temperatures above 2 Kelvin and below 2 Kelvin. What is this due to? I cannot tell you.
Sorry, I hadn't spotted the USR data really.
Yeah, it's not a difference between the two techniques. It is, I mean, something related to the system. Yeah, so there are data of MUSR up to 10 Kelvin. Yes.
Do you see any signature in heat capacity there? You have this slope break.
Well, as far as I remember, no, because there was no sign of anomalies down to very low temperature. Yeah.
Okay. So any other questions?
So this beta NMR, so you implant the lithium ion, and what is the composition to the inside? What is concentration? And can you use it in bulk or only in thin film?
Okay. I'm not a beta NMR expert, so I just basically the penetration is not let's say very deep, so it is of the order, let's say, of below micron typically. Okay. The concentration, this I don't know. I mean, I can tell you, of course, it depends on the production rate. This is the one that you have for the lithium, which is the highest one. I cannot tell you, you mean the number of these lithium nuclei you produce, let's say, per second and so on.
It's 10 to the 5, roughly, per
10
pulse.
to the 5.
10 to the 6, depending.
Okay. So 1 million per watt.
Oh, yeah, well, you can either pulse it, so you pulse it, and then you look at the SLR. So you can do it without RF. So you can look at T1 over T1, or you can plant it continuously. Then you get roughly, 1 million per.
1 million per?
per time. You implant
Ah,
continuously.
for each.
And then, no, you can also implant it continuously and do actually an RF experiment on it.
Okay.
So you implant it continuously your polarization, and then you implant then you radiate with the frequencies, and you can map out the cross splittings. So so you always very ultra dilute. You never have interactions with lithium to this question.
Do people do oxygen beta NMR?
No, like you have to produce it somehow. Copper and magnesium we do, or magnesium we do copper as planned.
Excellent. So if there's no more,
One thing, President, you said you can probe to 10 to the minus 15 seconds in some experiments. How do you do that?
No, okay. The point is that you can measure these time scales. For example, in high-density superconductors, if you take the parent compounds, let's say lanthanum-2CO4, from the value of 1 over T1, you can measure what is basically called Heisenberg exchange frequency, which is of the order of 10 to the 14. So you can access this time scale by measuring 1 over T1. Of course, you cannot measure at this very low time scale.
okay. Oh, Steve.
Just a quick one. Pietro, can you maybe just comment a bit on the different amounts of time it takes to do an NMR experiment and an USR experiment?
Well, I mean, there is a huge variability in the sense that it depends, of course, on the relaxation times. If you have a relaxation time which is hours, it will take maybe. But let's say that typically a study of the MUSR is usually faster than the NMR. Mostly because if you are based on the time scale of your relaxation times, the relaxation, if you want, the spin-lattice relaxation rate scales with a gamma square. And since the gamma of the muons is, let's say, for example, 3 times the one of protons, you have a factor of 10, okay? So, but this is just to give you an idea when it is more convenient, because it depends a lot on the type of experiment you are doing. You know, the NMR signal scales will be, let's say, about the square of the magnetic field. So if you're doing a high field experiment, you have a very huge signal and it is enough to do, let's say, a few positions. If you're doing low field, then you have a much poorer signal to noise ratio. So it's not easy to compare. But let's say in general, MUSR is a bit faster, and this is, let's say, you can reasonably do a set of experiments on a certain system in a few days, while with NMR it will require more time. But it is, let's say, very general.
You said it's true for solids. I mean, if you have liquids and do chemistry, sometimes a single shot is enough and you have all.
Yeah. Yeah, it depends a lot on the system.
Okay. If there's no more questions, then let's thank Pietro again.